Hi, my name is AG. I am a machine learning engineer and also an educator for Data Epic. And today we will be talking about machine learning, just the basics, the high level, the top of it. And this is part of like the applied AI with Python series. We'll cover like the uh, top of the funnel understanding of machine learning, and then we'll go in depth on like different aspects. But let's go over the for this course, or rather for this class, it will be just the overview and concepts like I mentioned. And we'll be talking about like intro to ML, the types of machine learning, then exploratory data analysis, which is called EDA, and then we'll also talk about scikit-learn. um like I mentioned, I feel like I'm reiterating it like multiple times, but like I mentioned, this is just going to be like a top of the funnel understanding of what machine learning is, which prepares you down the line. It's not, I would say it's not a very basic concept, so you have to like understand the fundamentals as you dive deep um into this industry or into this area. um so yeah. What is machine learning? Machine learning is all about giving computers the ability to learn and get better over time without being explicitly programmed to do so. Um, there are systems right now, like we have LLMs where you can just like go in, ask questions, and then it will bring out information for you, or generate an image for you. LLM is like the basic most popular one right now. And you have imagine you have to explicitly program that. You would have to like account for multiple conditions, account for like multiple um queries, like the inputs from the users that might come into play. You basically find yourself writing a very big system with conditionals if you are programming this like without the learning phase. Right? You have, or imagine you have to play chess. For example, you want to build a system that plays chess. You could either account for over 5,000 conditions or 5,000 moves as conditions in your Python program, and then maybe like, you see, it sounds like a lot. It sounds basic like a lot when you have to like consider having to program something like this. But machine learning just makes it easier. And with machine learning, you can teach the computer the moves. You can show the computer like um different moves that are possible to make, like strategies. Basically, you have the the board moves, and then the board strategies. You can teach that in form of like proper data to a computer, and is able to learn across that without you having to like um consider those large aspects that I mentioned earlier about having to explicitly program it. So uh, you can basically teach your computer to do all of this, um, as long as you have the right data for it. And machine learning makes this overall possible. And I think I can also go into like a deeper example where I would say like, imagine all those like chess games. If you play chess, I don't play chess, but I know enough just to understand the AI. So you want to play chess, and then they can tell you that, oh, you want to play like the small, is it easy, medium, and hard. I would assume that each one could be like a machine learning system that probably has more data than the other. Like for example, if you teach a child ABCD, and that's all. It's going to the child will probably be good at like ABCD and all of that, but it's just limited to ABCD. Now compared to a child that knows A to, let's say, L, right? Compared to a child that knows A to Z, right? Those are different levels of like data. So it's like, oh, I'll train you on these strategies, on this moves, and just minimal data, and then you have your easy level. Then the more strategies you know, the more understanding you get. The more strategies you know, more understanding. You get the concept basically. As long as you have your proper data set up, you can teach a system to do stuff. Chess, um, in finance, in medicine. In our example below, you can see like it's used for email spam filters. To Gmail already knows like, okay, this email that comes in, this is spam, this is not spam. It's a machine learning model that is like able to distribute that um, between your inbox and your junk folder or spam folder. And machine learning basically like learns the patterns and makes smart decisions on their own. Like this or that. Does this belong in this group? After watching Diad, will this person like Mission Impossible? Netflix recommendation. So machine learning does that. Like it's a very nice concept. As interesting as machine learning is, it is not the solution to everything. Like if you need to build a calculator, just build a calculator. You don't need ML for that. But if you need to build something like a chess game, like I mentioned earlier, or a spam filter, a recommendation system, of course you know that okay, this is the route to go. So machine learning is not the hammer to every nail or every problem nail. Yeah. Uh, so next part is two types of machine learning. There is the supervised learning. There is the unsupervised learning. So these are the two main aspects of what machine learning is. Now, what is supervised learning? It is where the model learns from labeled examples. This is like, as a student, you don't just go into exams, right? You are trained. You go to class, you read, right? You do like your internal assessments, those kind of things. You do all of that aspect, and then that prepares you to understand unseen um, information or unseen data rather, and then you're able to answer that. So it's just like I'm preparing for an exam as an undergraduate, and I have to prepare, read some textbooks, go over some classes, then do some past question. I am training myself on available data, so labeled examples, right? These are labeled examples I'm talking about. Available data that tells me this is a question, this is the answer, or this is a text, this is what it is about, right? Labeled examples, and then I can take that knowledge, go into the world, go into my exam, and then I'm able to like make proper I can prefer solutions based on what I know. So it can go into your exam or it can go into the world. So that's sort of how supervised learning is. You won't send someone that is untrained to be a doctor to go perform a surgery. So when you require that kind of like level of understanding, you want to use supervised learning. Then next part would be unsupervised learning. Now, what is unsupervised learning? Okay, one. So it is like where the machine finds hidden patterns in the data by itself. So there is nothing really to it's not learning for a future task, or it's not learning for unseen labels. It's understanding like the patterns within that data, and it's like this belongs here, this belongs here. It's just like how we mentioned the student that is gets prepared for an exam, right? It's like this student does not prepare for an exam, but goes into the exam hall and says, this. Imagine you have like 10 questions. You're like, oh, no, no, question one, question two, they are hard questions. Question three, question four, there are simple questions. Question 8 to 10 are extremely hard questions. Those are patterns that you have found as a person within an exam you didn't prepare for, and you're able to like categorize them. Okay, let me give like a more concrete example. In the medical area, so assuming you're testing like this experimental drug, you want to understand like, oh, how your patients like how your patients are responding to this drug, you don't have any information, right, really about it. So you assume you have like a data set of like um these people that are on this new experimental drug, and you want to like just group their vitals. So your you pass that through like an unsupervised learning system that can help you to like understand the grouping of those people within the um, experiment process. It can say that okay, this group based on their vitals, probably they are performing well, maybe their cholesterol is high, right? Or this group maybe like their blood pressure is low, or this group their blood pressure is like perfect. You now want to now look at, you can now, that basically opens the door for you to like say okay, if I look in this group again, maybe is it because of their ages? You can ask questions like that. It opens the door for questions that need answers to, right? Is this group that is performing well, is it because of their age, or is it because of their skin, or is it because of like maybe their height? One random aspect, but it just opens door to answer questions like that, and that is an example of how you use unsupervised learning. And that example will probably be like a farmer that maybe like has multiple lands, assuming like 1,000 lands over different areas, and then he is collecting like soil samples, weather status, then maybe like satellite images, those land data, and it passing that through like an unsupervised learning system helps the farmer to like say okay, maybe this is the best farm based on the patterns that the system has been able to deduce. Is able to like say okay, this group, maybe I can do maize here. That those are things that it can answer for you. So that's the concept of unsupervised learning. um, and it just looks within your data, finds patterns, uh, basically like solving like a jigsaw puzzle without looking at the end goal. So it's like a neat process. So each of these type they have their specific use cases that you can have them for. So let's go one more step into the class unsupervised learning. What is unsupervised learning? It is the process where hidden patterns in the data are found without any labeled example. It's like going into the unknown and segregating what could be similar within them. The algorithm discovers structures on its own, grouping similar items or reducing complexity. I'll do okay, yeah. Basically, grouping similar items and just reduces the complexity of your data. Like it helps you like understand, those questions that you might have, and it's like organizing a messy drawer without instruction, pretty much. I have this little. Oh my goodness, I have this little spoiler alert. Unfortunately, uh, all right. I have this little analogy um, that says like similarity finds its own company, just to like emphasize the point. And then there are questions understand unsupervised learning can help you answer. And it can answer questions like, oh, which customers are similar, which what are the natural groupings in this data, can we simplify this complex data, what is unusual or doesn't fit the pattern, answers those, what features matter the most. It can answer all those like questions for you, those open-ended questions, right? Unsupervised learning will like do that. And a good example of those um, would be customer segmentation for marketing. So imagine you're an ISP, say like MTN or Etisalat or maybe AT&T, and you want to like maybe like group your customers based on maybe like certain behavior. Customer segmentation for marketing. You want to know who to target for with certain ads. Unsupervised learning will help for that. You want to do anomaly detection, image compression, recommendation systems. Recommendation system. You don't the when you first log into Netflix, they don't really know like what you want, right? It just like they give you just like a random set, um not so random, but they give you like a random set, and then you start watching one show. They understand you one bit by bit as you watch more shows, because oh, less this person likes to watch sci-fi, and then you get those sci-fi recommendations. Unsupervised learning does that. Gene sequence analysis. This is just in the medical field. Market basket analysis, e-commerce area. So, what is clustering? This is just a slide that shows the unsupervised learning in action, right? It's like finding natural groups in data without labels. So it's like, oh, look into this like set of data that I have no label for, and understand the patterns and then cluster them for me. And it's able to like cluster like, oh, these are circles, these are circles because maybe the pattern it found is like the rounded uh, surface, or maybe for squares is like, oh, they have 4 points, so um those are the squares, and then it does the same for triangles and say, oh, the pattern I found is they have 3 points, right? um So we this is just like um unsupervised learning in play. And I should also mention that it doesn't really like label your data. It doesn't label it in the sense that oh, this is squares, this is triangle. No, it just helps you cluster them, and then you can label them based on the patterns that you have seen. Okay, these are the LD patients. These are the people that have high blood pressure spiked. These are the people that have high cholesterol. Those kind of things. It helps you to um, understand that. So that's basically like the overview of unsupervised learning, and I hope you get it. Um, okay, for next part would be supervised learning, the part where the student prepares for the exam, and um, it's just like, yeah, like I mentioned, it's just like students preparing for a test using past exam papers. The model learns by making a guess, checking the correct answer, and adjusting itself to reduce the errors. Me, there was this course I had to do in my undergraduate days, and it was I think my first year, so I wasn't familiar with how my school set their questions. How do I prepare? I need to learn. I can't unsupervised learning my way into the exam, or else I'll fail, right? So I have to, understand this thing. I have to supervise myself to learn, and with labeled examples. So what did I do essentially? I looked at my notes, then I went to look at past questions, and I was like, okay, after reading, I would try out some questions in the past question, see how well I do, and then I know that okay, this is the part that needs improvement, and then I improve myself, and go back to the notes, understand some things better, go back to do the past question, and maybe like more questions, more unseen questions, and introduce myself to more unseen questions as I do better at earlier ones. So all of that concept is how supervised learning work, and that is why it can learn to play chess, because what it does is it trains itself, like it's trains itself on the data, like understands what's going on. It makes those guesses, and it's like, okay, this is wrong compared to the answer key that I have, and it's like, okay, let me reiterate some things, let me make it better. All right, so that back and forth correction until you are good at something is what actually happens within the supervised learning um, system. So, um, yeah, and it is the process of training a model on a labeled data set. We give the computer both the input data, which are the features. So this is like your notes and your past question and your classes, and then the correct output target, which is probably like that to the answer to your exam question. So features are the input, target is the thing you are learning for. And its goal is to learn the rule that maps one to the other. How does this correlate with this such that I can understand it on a new sample? And there are two main types of supervised learning. There is the classification, there is the regression, and supervised learning problems are generally categorized by the type of answer we want the model to predict. We can say, are we looking for a category? Are we looking for a number? And that is where this classification and regression thing comes in. I'll explain better. So, you know how I mentioned like two types of supervised learning and how they are called classification and regression, right? So, what is this difference? Um, Imagine your state governor. He comes to you and he says, "Oh, I want to understand my people more. I want to understand my people economy better." He wants to know their social status based on maybe like the data that the government has. Probably like maybe things around your salary, maybe things around your the area you're staying. They basically have those government data, essentially. And it's like, oh, okay, I want to group these people into like certain classes. And then it's like, um, what are these classes that you are grouping them into? Like, there's the social class, right? Social status rather. So we are looking at a certain number of classes. There's the um, lower class. There's the middle class, and there's the elite or upper class. Yeah, upper class. So there's lower class, the middle class, and the upper class. And this is just like a finite number of things that we are predicting. So we have like, let's say, 1 million people in this particular state, and all you have to do is learn based on their data to um, group them into different classes. Of course, the government would have done this before, so we are training our model on that um, old data, and setting it up with new data, because there's like maybe the data that we have is from 1960 to like 1999. Right, let's get the new century, the millennium, um 2000 to wherever 2025, I don't know. Anyways, so um it's like that, and then you basically get that new data that your governor has given to you, and then you're like, okay, I'll look through this data. This person, upper class. uh this data, this data, this person is middle class, and so on. That when you have that finite set of things that you're predicting, then you have a classification problem. All right, now if your governor now says, I want to see the salary projection for each of these data. All right, I want to see the salary projection um like in 10 years. Like, how would this salary look like in 10 years based on this data that you've given to me? Note that, of course, we still have previous data that is already labeled, and we're just trying to look at new data. All right, so um when you ask predict salaries, right, each person each person has different salaries that they'll be paying. In fact, it ranges by a lot. So me as a person, I can be collecting like $200 million manifesting. I can be collecting like $200 million um per month, right? And another person can be collecting like um $150 million. Another person can be collecting like $10,000. Another person can be collecting like $30,000. Another person can be collecting like 33,500. So there's like a plethora of options that you can get, because salary is not just like one single value, right? It's not like a finite set of value, right? Imagine you have to like write out salaries of every single person in your state. That number will range, like seriously range. So when you have that seriously range situation, you already have regression problem. And once you start playing with the data more, once you start like getting hands on like data, doing some machine learning stuff, it will come easy like breathing to understand like, okay, this is once you just see the data, you just know, okay, this is a regression problem, this is a classification problem. So it's, don't worry too much about like not diving deep now. We would definitely talk about that in our future classes. Uh, all right. So regression predicts continuous numerical values, and the question is always like how much, how many, all right? An example is predicting house prices based on the square footage or forecasting next month's like sales revenue. So these are two applications. I also mentioned one more application like in like salary and stuff. So once you have that big range of targets, regression, finite, classification. All right. So this is just like a sample, a data sample of what you might see in the real world. You can probably have more columns and more rows, but this is just like a sample. And you have we have um, four columns, and we have this like features data which we also call input, and then we have the output label. So and then the model learns the mapping patterns. Machine learning is all about pattern finding, right? So it's like um it finds the necessary patterns, and then it's like, okay, based on this data, this is a medium price category. Based on this data, this is a high category, and so on and so forth. So you always have this like set of data, and which are features or input data, and the model would predict the target. So it could be anything as long as it's a target. It could be a finite set of things, or it could be like a range of things. So whatever it is, finite or range, it's a target. All right, it's we're targeting the output. So yeah, that's pretty much it. This is sort of what you would see in the real world. Um, in terms of like data, you'd always have your input features, you'd always have your target column, as long as it is a supervised learning problem. So just to organize our lingo, or rather our understanding of certain machine learning um, names, or machine learning, yeah, machine learning names, pretty much. We have features, we have target. Another name for features would probably be input data, or like independent variables, right? So if we hear features, if we hear independent variables, if we hear input data, you're thinking um, the same thing, pretty much. Um, if you hear target, if you hear dependent variable, if you hear output or label, then it's all the same thing. But I like to use features and target because independent variable and dependent variable are so mouthful. Yeah, features and target. But you can pick whichever one you want. You just know whatever people are talking about when you hear them speaking about it, or when you're told, or yeah, you just get it pretty much. Um, so there are data requirements for modeling. Basically, how would you prepare yourself for this exam? You don't want to just read halfway or read the wrong thing. Imagine you have like, I did that before once actually, where I had an exam called AEC. The course code was AEC 303, and we had another course code that was like AEC 301. I didn't label my material as well, so I read 301 for a 303 exam. It was a multiple choice exam, so I passed it eventually. I feel like I used up a lot of luck for that. But anyways, yeah, you want to ensure that your data is proper before you pass it through any machine learning system. And what are these requirements? What are these basic requirements? You must have sufficient quantity of that data. So large enough data set for the model to generalize patterns to understand like more stuff. Like, oh, there are more strategies. Remember that chess example I gave to you? It's like this. So imagine you have like 1 million strategies in the world, arbitrary number. You have 1 million strategies, and then you now have um, let's say your strategies are within a data form, and um, you pick a machine learning model. So assuming you pick a machine learning model and then you send like 20,000 samples from your 1 million. 20,000 samples is a lot. It's quite a lot, right? It's it's a lot um, for data, but and it also helps your system generalize more. Now imagine you now increase from 12,000 to like say 500,000, right? Your model is like, like I mean that's like that's how I be when I learn new things, and I'm like, oh yeah, like I believe those ML systems just like go, oh, like yeah, this is new stuff. This is like added to our brain memory complex. Add it to our memory complex. So we um, the more data you have, the more generalizable your model will be, and that means that if you plead um, your model that has 500,000 samples versus your model that has 12,000 samples, like almost every time, if not all the time, the guy with more knowledge would win. Now imagine the big guy now comes that now has 1 million strategies, and that is like the hard level guy. He will almost always beat the lower two guys. So the more your data, the more you can generalize stuff, right? And then you want to ensure that your data is like high quality data, free from errors, duplicates, irrelevant noise, right? Missing values. When I say like relevant noise, imagine you have like a system, maybe in the government data that's in the people data that your governor gives to you, and you have they have this data, right? They've had this data for many years, but they forgot to do some things. They probably forgot to, like, maybe someone passed away. They forgot to update that this person has passed away. So their age is still counting every single year. And then all of a sudden you are seeing in your data someone is age 248. Now that's the problem. Like, I would not train my model on someone that on a data point that has an age of 248. I will investigate that data more and see what is going on there. Because under no circumstance will that data point be my model. It's not possible. Right. So you want your data to be high quality and clean. It's basically garbage in, garbage out. You throw garbage into your machine learning system, it's beans that is bring out for you. So garbage in, garbage out situation. Yeah. So and your data must be relevant and representative of your problem, right? Um, Data must accurately reflect the real world problem space and population. You are not building this, most ML systems are not built as like side, they're not built as basic things. They are used in the real world, in medicine, in finance, in e-commerce. Like, mention all these things, you will find ML being used there. So you have to ensure that whatever scenario that you have to like train a model for, or train a model in, whatever it is, you must ensure that it is representative of that problem. You can't have like data that um a you can't have like data on medical people, and like you want to use this in your in on animals. Why would you do that? Like, a vet doctor is different from a medical doctor. You know, ensure your data is representative. So it's like this, and also like when I say is representative and relevant, it's like ensure that it's in the right place and ensure that it makes sense, right? Imagine it's just like your model is like a baby, pretty much. You can teach it to walk, you can teach it to like jump, it will jump. You teach it to walk, it will walk. Now, if you teach your baby to fly, is that really representative of like real world problem space? Can babies fly? Right? Eh, Teach a baby to fly, and we know very well it can't. It will always fail. So you have to ensure that your data is relevant, and your data is representative, has that representative um, um, sense of your problem space. So, and point four, it has to be structured, it has to be organized. All right, it has to be in a usable format with clearly defined features and consistent types. So if you look at this sample, you would see that, look at this picture. This is our size in square feet, and it's like you see all of these are numbers. You don't just see like a random ass like 1,500, 2,000, and then you just see like A, B. No. Or look at this location. It's a suburb, it's a city, it's a rural area, it's a suburb. The data type must make sense, right? Must align, must be well structured, right, and well organized. And then you must have accurate labels for supervised learning. When you have to label your data, you must ensure that your label is correct. Like I said, garbage in, garbage out, and you don't want to use garbage in the real world, right? Ensure that the data that you are even that has already been labeled that you're training on is correct data. And this brings us to EDA. And I was referencing garbage a lot. Like, how do we even avoid this garbage? This is where EDA comes in. Exploratory data analysis, another mouthful term in machine learning, but I'll just call it EDA from now on. Yeah, so EDA. What is EDA? EDA is like getting to know your data before jumping into modeling. It's just like preparing for that exam before going to write the exam, and you have to prepare well. You want your model to be good. This is the part where like 70%, most of the time, you rarely see systems out there that are like 70% and they are used in real world. Most models tend to like, oh, if it's actually like a proper problem space, you want to be seeing 99%, that accuracy, right? I feel like Gmail can probably boast and say that like their system is like their spam classifier is like 99% accurate. That's kind of model we want. That's kind of like, you know, that's kind of model we want basically. So the one um that has understanding of the problem space, and is able to give out correct labels, and correct outcomes in whatever case that is applied to. So to ensure that EDA, know your data before you model the data, before you pass it to like a machine learning system, and then you spot trends, oddities, that age when you see age like 238, mm, mm. Then then it helps you understand like what's really going on within your data, and you get to see what I mean, right? So doing a good EDA means your models will have like solid foundation to work from. So why is this necessary? Why is this crucial? How I mentioned like your data must do this. EDA sort of like gives that outcome of data that fulfills every data requirement before modeling. And why is it necessary? Um, it ensures data quality, ensures that your data is cleansed before being used to model. So it helps spot missing values, errors, inconsistencies, and that must be fixed. Without this, your model will learn from noisy, unreliable data, leading to poor predictions. You don't want to use a poor um, data, poor. You don't want to use something that is not like um, that has poor ED analysis, right? I just said ED analysis like a tautology. Poor EDA, and use that in the real world. No, we really don't. So it's important. In fact, I should also let you know that while being a machine learning engineer, machine learning engineers like data scientists, they spend 80% It's just like the general metric, the average metric. You they spend 80% of the time doing EDA, and like the rest doing modeling. You see how important EDA is. So with EDA, ensure data quality, identify outliers, like visualizing data reveals extreme or unusual points that don't fit the pattern. Ignoring this can cause models to skew their learning to accommodate them, which will reduce like overall accuracy. And it's like you should know that when you are doing this machine learning and you have all this data, you're not just looking at rows and columns. You can see them, you can visualize them, right? It's just like seeing a. You can visualize them basically if you know what pie charts, histograms, um, those plots. That's data. That's data viewed, right? That's data visualized. So you can actually visualize them, and then that can help you to like see things better. Like it's just clearer, right? So and then you can um, ensure that like all those unusual points that don't fit the pattern are out, and then um, ensure that your accuracy is not reduced, that your model accuracy is not like tampered with. And then one other thing with EDA is like it can understand distributions. Like it knows, like knowing how your data is spread helps select the right model and create better features. Help select the right model. That sort of this is like an Easter egg of machine learning. And it's just like saying like how we talked about unsupervised learning and supervised learning, right? There are different algorithms that um, are under these learning processes or these learning types. There are a lot of algorithms. It's not like there is no one fits all, right? So you have to like understand the algorithm, and because that would help you like you have to understand your data, understand your algorithm, and you just know like which algorithm like fits your data for that use case. So once you understand distributions, it can help you like know, okay, this is the right data I want to use. This is the right model that I want to use for this particular use case. Right. Okay. So these are common EDA plots and their purpose. I mentioned histogram. So this is there are still others, but this one is just like a um see into EDA, see what goes on in EDA. Like see those samples. You know, yeah, things you would do in EDA pretty much. And one of them is like histogram, the shape checker, and it's like it shows the distribution of a single variable, um, and answers the question: is data skewed or is it centered? This kind of thing. So it's like if you have this kind of like view, this kind of like histogram view, um, and you have it for a single variable, right? So imagine you have like let's say people that how we did those lower class, upper class, um, middle class. We can use an histogram to plot them so that we can easily visualize. We won't go through each row. Imagine you have 1 million people in that city or in that state. You would not want to go through each one and be using hand. You would want to visualize. There are systems that are available for us to do that with in Python, thankfully. Um, so the Instagram can just like sort of show the distribution and count of those variables. So if I want to say like the number of those classes, I can now say, oh, governor, this is what I found out. This is um, this is the number of people in the lower class, and then I'll just show him on the bar chart. I won't show him my data set. I'll just show him on the bar chart, like him or her on the bar chart, like yo, um, this is um 500,000 people are in the lower class, 4 million people are in the upper class. You're able to say those things confidently because you can see and you can show. So you would use Instagram for things like that. So the other one we'll go for is like scatter plots. These are Like I mentioned, these are common EDA plots. And it's like this. You want to like check how two data points are relating to each other in real time, or like rather in real action. So it's like plot two continuous variables against each other. You know how I said that uh stuff can range, data can range, your targets can range, right? Also your inputs can range too, right? So, because your input can range, we are not saying it's a regression problem. It's only the target that defines that. Your target defines whether it's a classification problem or it's a regression problem. Um, so we now have scatter plots. When you now see something like continuous variables, those are the range stuff. Data that ranges, you would want to scatter. You want to use a scatter plot for them. So it's like question that answers as x goes up, does y go up? Does y go up too? So an example that I can show you is this. This is an example of a scatter plot. So this the title of this is daily temperature um, and visitors for 90 days. And we, sorry, and um, we want to see the number of visitors against the average temperature. Now, this the kind of data they range. On the y-axis, you see number of visitors. Visitors range. Average temperature ranges, right? So these are now, you could now say like, this just satisfy the point of continuous values, continuous variables, right? And if I was to read this for you, right, I would say okay, so this is average temperature, right? This is 80, 85, 90. Okay, so the temperature is increasing. Man, I hope this is not in degrees, but anyhow, this the temperature is increasing, and for some reason the number of visitors are increasing. Because why would you do this to yourself? Anyways, that doesn't really matter. It's just from this scatter plot, I can say that data, if I go to 80, just let me see, at 80 degrees, I will say that, let me see, roughly maybe 170 people came. Let's go to 85 degrees. We will not consider the middle ones because it's just easier. So 85, let's say 85, maybe like 180 people because it's just right above. Okay, let me show you. I don't think you can see my cursor anyway. Let me show you my cursor. All right. So we should be able to see my cursor now. So you have this like 85, and I'm taking this against like the y-axis, and you can see like roughly 180. Roughly 180 people came. It's just right above this one. And let's go to 90. 90. Wow, like about more than 300 people came. So we can see that as temperature increases, like as 105, 600 people came. So as the temperature increases, the number of visitors are increasing, and that is the cool things Catapult can help us do. You can say that, oh, so temperature and visitors, they have some common relationship. That's what EDA can help you do. Really cool stuff. Um, yeah. So okay. So one other thing I mentioned is the data centered? Is it skewed? This was what like caused me to pause earlier, and I was like, oh, I think I missed explaining this. So when you say data is skewed, um, it's pretty much like, oh, let me show you that. So this is a this histogram. I don't know if you can see my mouse. Okay, you can. So this histogram that I have here, this is not skewed. It is well distributed, like it's evenly distributed, in the sense that like everything builds up to like a triangular, like a proper triangle, a balanced triangle. I've forgotten the name of um, those triangles that have equal sides. Hmm. Anywho, equilateral triangle. I think that's it. Anyways, I digress. So is it skewed? It's like, is it well balanced, right? So then is it centered, right? So these two questions are sort of like the same thing, like it's the same um, scope. So is data centered? Is it skewed? So when it's centered, it sort of look like this. That means that your data is evenly distributed. Is it skewed? Maybe like it's moving to the right more. So let me quickly show you what skewed data would look like. Um, a skewed histogram. Yep. So you can see this. Um, let me put this on a bigger image. So this is something that is like um, this is right skewed or a right skewed histogram. Yeah, this is right skewed. Let me see if there's a okay. This is a much better image. So this is a right skewed histogram, and this is like a left uh skewed histogram. You can see like most of the um, most of the data is climbing from the left up, and um, most of the data is coming from the right up. It's not even to the center. Like if it was a balanced one, you would see like the high histograms. You see them maybe like around 3, 4, 5, right? Not at the extreme end of one or the extreme end of six. Those are skewed data. So once you want to know whether your data is skewed or evenly distributed, it's like you understand your data range. You know that okay, maximum value is 1, minimum value is 10. I feel like I said that backwards, but yeah, minimum value is 1, maximum value is 10. And maybe you have your data on, that range. And when you like plot that, you view it based on whatever um, variable you're picking. You can now say that, okay, hmm, this data seems to be right skewed. Something, well, data being skewed doesn't really mean there's a problem anyway, right? There are times when a skewed data is okay. There are times where an evenly distributed data is okay. So there are times when you want to like balance that out. So that's why I said like once you understand like the core of EDA, you will be able to understand how to use the right model. Fun fact: for a right skewed data, I will probably use a different model, a different like machine learning model or machine learning algorithm uh, to train this data on, right? For Dan, maybe like for like a left skewed, I'll probably use like a different model for that. So this is what the skewed data looks like. And this one is like right skewed. And you can see from the initial one, it's sort of right skewed. This is like the median should be maybe like towards, anyway, you can see this curve, right? It's leaning towards here. So um you just know okay, this is right skewed data, right? So um you would probably like skewed data. You'd probably be okay with like skewed data um when people with blood pressure, right? You put that on it. You put maybe you're plotting a population of blood pressures of people, and then your data is like it's probably like people who that have high blood pressure would be really low. So your data will probably be left skewed in the sense that not everybody will have high blood pressure except it's a really bad economy. But anyway, you'd just find out that um, that data is really low at a particular point, like really, really low. It's not, there is no balanced trajectory, like there's no, there's no even distribution of blood pressure, right? Like I said, except there's something really wrong with that, like economy or maybe the data, but we'll assume it's the latter, it's the data that probably has issues. Um, so if like blood pressure is evenly distributed, like yo, what's going on here, right? Why is everybody okay? You know. And skewness is also fine on data feature like salary. So people earn more than others. There's no like even distribution. Like people will definitely earn more than others, while people earn really less. Others are very really high. So imagine you're plotting um, data of like people that are civil servants versus CEOs. That data will be really skewed to one point. That data will go high at one point, depending on the range. So um, yeah, it's pretty okay. Let me use this for example. So um, this is this is let's say we are assuming that we want to differentiate between like salary and blood pressure, right? So salary basically like increases. This is going to be like a left skewed problem. For blood pressure, um, yeah, you'd probably see it as maybe a right skewed problem. If you're like having people like old people, young people, um, youths, babies, right? Their blood pressure will be pretty low. Um, on the other side, and maybe like old people will have like they are more susceptible to high blood pressure, so they would have that higher count. So that would be like a right skewed situation. But it just depends on how you arrange your data on your x-axis, pretty much. So yeah, but I hope you get the point of what data skewness is. We would take a much deeper dive into this in future lessons. So we have talked about histograms. We've talked about like data centering and skewness. We've talked about scatter plots, how it's like with continuous data, and then we'll talk about box plots, the anomaly hunter. So it's like it shows the spread and spots outliers. Um, you know how I mentioned that age situation. If you put that on a box plot, um, the box plots would easily identify. So it's not like you're saying that, oh, I want to write a condition that checks this max age. There's no really max age. Someone can be 110 and still be alive. That's very possible. You can't assume that person is dead, but you can say that okay, um, maybe people in this area they live long or something. I don't know. I don't want to make guesses, but if you put that on a box plot, it will help you identify that these are extreme ages and these are very very low ages, right? You want to know that within your this data in your box plot is proper. Let me show you something. So I will show you this one. This is a box plot. This is a box plot. So what I'll just tell you the structure of a box plot pretty much, because as you can see in this data, this is pretty much, you might have heard of histograms, heard of scatter plots, but box plots look different. So um yeah, so for box plots, they have this setup, this design, right? There's the minimum, there's the maximum, there's this whisker, like the syringe, in the when you're pushing the syringe in, you can sort of have that part that comes out and goes in that area. You can call it like the whisker. So we have the minimum, we have the maximum, we have the whiskers between them, and then we have the um, interquartile range, mouthful, and then we have the lower quartile, upper quartile, and then we have the median. Median you would have heard of, right? Um, but not so sure about IQR. So I will show you another one. So this is just the basic structure of what a box plot is. Then this is a box plot with outliers. Now this is now the place that I would now mention IQR. So we have the minimum. You can ignore these formulas anyway. We have the minimum, we have the maximum, we have the whiskers, then we have the median, right? This time we have the outlier and then we have the IQR. So median is like basically the center of your data. Like if you have like a age data, your median would probably be like the middle, of course. The median will be the middle value of that data set. So if you know the middle of the value, you know you can easily like intuitively understand probably like the minimum and the maximum at that point. So using one value to get the minimum. But I don't want to dive into it right now. We would talk about that later. But median is just the middle of your data, right? Like the center of gravity of a data. I like that example. Um, so when you have the middle of your data, IQR is just basically saying these are the usual points, or these are the usual occurring data points in your data set. So IQR is that the bigger it is, the more usual data points are, the smaller it is, the less usual data points are. So that's just IQR basically. And um, I just said I should have said wider and narrower. Anyway, but like the wider means usual data points. Um, narrower than not much usual data points, and then you have the outliers. So because you have your minimum and your maximum, let's say your mean age is like 23, your max age is like 20. Your max age is like, let's say the you want to know people that are still working. You probably want to you probably have like maximum of like 65, I think. So assuming your minimum is like you must have when you the age, hypothetically speaking, hypothetically speaking, um, the minimum age to work in this probably our system would say is 20 years old, and the maximum is 65. So you can only work for 45 years. These outliers would mean that these people are less than 20 years old and these people are more than 65 years old. And that is how you can easily identify outliers, all the data points in our system. So pretty much that's just the concept of box plots. We'll take a deep dive later in another class. So are there any extreme values throwing our average off? Average being like IQR, like are there extreme values like you really should not be here, sort of thing. So box plot will tell you that. And then we have the correlation map or correlation heat map, and it is like the color coded grid showing how strongly every feature relates to every other feature. And it answers the question which features matter most. A lot of things to unpack there. One thing first, it's color coded. I like colors. Um, it tells you it is one feature versus another feature. Remember how features are, right? Do you? Independent variables, inputs, right? Anyway, um, it's color coded. It's one feature against another feature, like you know, one feature against another feature, and you know, there's now that relationship. So three things: color, feature against feature, and relationship. Which features matter the most? Now, let me show you um, what it looks like. So, I have this little um, drawing of what an histogram looks like. And this is what it would look like in real time. Well, this is another box plot. Well, I feel like I'm digressing. This is just one. This is a traffic source data view. Probably like, yeah, traffic source, whatever. Maybe this is for Shein or AliExpress or Amazon, whatever. And they're like showing like, oh, how how many lifetime orders, like where did they come from? And then you have the minimum, the maximum. The usual data points is like around 3 to 5. The organic people that came to the Amazon website or whatever it is, that have the lifetime orders. There's the minimum lifetime order um, of maybe like 3, and the maximum being 23. And then the usual data point is between like people that are organic. The usual ones are between like 4 and maybe like 12. You know, that is what boxes can help us do. There are no outliers here, so we are fine. Are fine. Anyway, correlation, right? this is what a correlation map looks like. Um, it's color coded, it's feature against feature, and these values are the relationship um, that I'm telling you about. Now, let me it ranges. Let me explain this. So it ranges from um, -1. So the relationship, right, ranges from -1 to +1, right? That is the relationship of feature to feature in a correlation map. And you see all these values are 0.41, -0.7, you know, none is greater than 1, none is less than, or yeah, none is less than -1. So what is this? We have these features. We have sugar. Okay, so the data says that this is a relationship between food and health. Um, we have calories, sugar, sodium, fat, cholesterol, health outcome. Oh, I should mention that correlation maps, they're not like they're not like staircased by default. They look more like this, but you notice the staircase anyway, because like if you look at this is variables of Palmer penguin data set. So it's like a penguin data set, and it's like their body structure and mass and stuff. Um, so it's like bill length, I guess it's the beak, and you'd see bill length to bill length. Of course, like your correlation to yourself is always one. Like yourself is yourself, but when you bring in an external factor like you and Sandra, for example, what's your correlation between you guys? Um, say um, Elon Musk and Donald Trump. What's their correlation? Like two features, right? So um, yeah. So this is just like a more sanitized view of what the map looks like, so that you can understand this basic stuff down through to you. So you have all these features, and they're the same ones that are down. So it's just like feature against feature sort of thing. So by the time calories meets calories, it's going to be one. We don't that doesn't matter to us. We already know that. But anyway, so let's see calories and sugar 0.44 closer to one, right? Um, if it's closer to one, it means they are positively correlated. So probably like um, if one increases, the other one increases too, right? It's positively correlated. If it's closer to -1, it means it's like negatively correlated. So as probably one increases, the other one reduces, something like that. So this is a positive correlation, and the correlation is like calories to sugar is like 0.4. So probably as your sugar increases, you probably have more calories, or you can see the other way around, like more calories, more sugar. Then there is a strong positive correlation between calories and sodium. Very strong. This is one. Like more calories, more sodium, right? Then there's like calories and fats. There's a high positive correlation between them. So it means these calories positively affect all these features. Then we have the health outcome. The calorie doesn't it doesn't really matter to the health outcome really. So um yeah, we could say that yeah, the calorie is negatively correlated to the health outcome. So whatever happens to this one doesn't necessarily affect this per se, in that sense, or maybe like it affects it in a negative way. That's also one thing. Yeah, we'll say it affects it in a negative way. So the more calories you have, the lower health outcome. And then you have sugar to the rest of the gang. You have sodium to the rest of the gang. You have fat to the rest of the gang. So yeah, fat, cholesterol, pretty normal. Oh, I should mention that correlation does not mean causation. Like correlation is just within your data, because your data is saying that, oh, because calories negatively impact health outcome, does not mean that in the real world calories you know impact health outcome. It's just within your data that is happening. So correlation does not like necessarily mean causation. Like don't confidently say that because your correlation map says this, that this is what is happening in real time. No, this is what's like you if you eat calories, your health outcome, reduces. Don't that's causation. Do it in the concept of in the area of your data, right? Limit your correlation map explanation to your data, and don't confidently use it in outside of it. And that's why that time correlation does not mean causation comes into play. So we have this, yeah. So I'll just briefly read this one. So the year and the bill length, though they don't really like the year and the bill length rather. They don't really like correlate to each other. It doesn't really have much fact. This is even closer to zero. So that means this doesn't really affect it. Like one can be going up and one can be going down. It doesn't affect anyone. Like if it's closer to zero, they don't one can't sway the other really. Yes. So closer to zero. But when you have stuff that is like very large, see this one, body mass 0.87, what does it correlate to? Their stuff is distorted. So I assume if I look at the vertical side, I assume so bill length, so two steps from here, one, two, so here body mass, so flipper length, so flipper length to body size, body mass. So in penguins, flipper is that they are like feather thin, their arms. So is this a strong correlation that says if the body mass increases, then you have like longer, um, longer flippers. So there's a positive correlation. You can see correlation is this one's correlation is from 1 to -1. As long as it stays between that range, your correlation can is okay. Like you notice that this one is between 1 and probably like -0.5, or but this is one anyway. This is one. Sorry, this is -1. So anyhow, so 1 to -1. That's correlation. Um, pretty much. So all what the correlation just and what this correlation just tells us is all these features matter in some way. So like some are negatively correlated, like all features matter. This one we could say that maybe this one, if year, let me see year. This is year, right? So year has like close to zero effect correlation on all the other features. So technically, like you can discard year. So this year is not necessarily important to the body structure of the penguin, of this penguin species, Palmer penguins. I wonder how they look like. Let me just digress here. Palmer penguins. Penguins. Midges. Okay. Yeah, they look cute. They look good. Uh, Back to class. So we've talked about all of these common ones. There's pie charts. There are a lot of them that you could use, really, that you can plus. But these are the common ones, and because you understand these ones, it's not hard for you to understand the rest of them. That's the good part. It's just like watching season one of a movie or of a TV show before going to season two. Always start from season one, please. Like anyway, I've you know what? This keyboard is messing with me. All right. So next part is introduction to scikit-learn. Our last part of the slide of this class, our last section of this class. So what is scikit-learn? Scikit-learn is a popular Python library that makes machine learning easier. It packs a bunch of handy tools for building models, whether you want it to classify, cluster, or predict. You don't really have to write your algorithms from scratch, because like scikit-learn, for most, um, unless you have a very niche use case, very niche use case, I have not really had to write my own machine learning algorithm. Maybe not yet, I don't know, but over the years I've not had to use that. So whenever I want to model and I know the word I want to use, I just go to scikit-learn, check the tool that I want to use to build my model or do whatever I want to do, and check that it exists and use it. Simple as ABC. Like that's what scikit-learn does. It just makes it easier for us to do ML stuff. Uh, so what is the basic syntax and structure? So I'm assuming we all know Python, right? So using scikit-learn is like is pretty straightforward. You import what you need. You import maybe like you import what you need pretty much. You load your data, right? You pick a model and then you train it using a few easy commands with fit and predict. And this clear, consistent syntax helps you focus on solving problems without getting lost in your code. So after you like maybe this load data, imagine this is assuming that you've done ED and you pick your model. And when you want to pick your model, when you pick your data, right? You fit your model to the data. You're just calling that model dot fit. And when you want to predict on new labels, dot predict. So if you are doing supervised learning, so just simple as that. You don't have to write like super crazy algorithms, and that is the joy of ML. We have simplified tools for algorithms. We have simplified systems for learning situations. So you know how I said like there's always like a load your data, import what you need, load your data, and pick a model, then train it with fit and predict. This is the 3-step API. So it's 3 steps. So imagine you have your um, whatever use case you're using it for, whatever machine learning use case right now, be it supervised, unsupervised, and uh, whatever. You check the sklearn um, library. You check where you want to import from. You import what you need. You import the model. So you create an instance of that model, and you just fit your data. So this X train, Y train, I wouldn't go deep into it, but it's just basically like um, the input. Hey, yeah, sorry. I'll just like give you high level. This is the input. This is how the input and label look when you are training the data. All right. Yeah, this is how it looks like. So it's like saying these are the input variables for that data. This is the target for that data. So this is what you're learning. This is your um, notes. X-ray is your notes, your classwork, whatever. And Y train is maybe like your past question, right? That already have answers. So you use that to answer the past question, and then because you know the answers, you can basically like, oh, let me go back. I missed this set of things. Let me go back and learn them and understand it again, and then try to do it again. So that whole iterative process of getting a good model accuracy is why you need this X and Y. And they're just variable names anyway. X train, intuitively, X that you use to train data, Y that you use to train the data. So so this is just like input variables and target for learning. So the model learns patterns from your training data. And then the predictions phase, assuming you're doing like actually you can use predicting like the different forms in supervised and unsupervised, because like you're predicting groups too. Like, anyway. So you just take your model, you just take that same model that you've trained via fit, and you do model dot predict. And this x test is the variable of data that your machine learning model has not seen before but is about to label, given that it has learned from a previous quote unquote learning phase. So, and here you're now using the trained model to make predictions on new and unseen data. And this pattern works for scikit-learn estimators, classifiers, regressors, transformers. You got it. This is the 3-step estimator API. So let me show you what scikit-learn looks like. So this is, if you go to scikit-learn.org, you see like their system, their page, and you see like you see classification, regression, you'd see um, clustering, this that I want to talk to you about pre-processing. This is some EDA stuff. So um, yeah, so I think I mentioned like so let me show you um, so let me show you the user guide briefly. So I'll pick maybe like linear regression. So let me say logistic regression. Anyway, um, so this in scikit-learn they would explain the algorithm to you. I'm not taking a deep dive into scikit-learn right now. But I just want to like show you like a sample in their documentation where they show you how to use the API. Yeah, so from sklearn import the family. Although this is sort of from sklearn import family, then use family dots, but it's pretty much still the same. Sklearn the family import models. What they're just doing from in their own documentation is from sklearn import family, then family dot model. This just looks cleaner, please. Um, yeah, so you just call your model, initialize it with whatever you need to initialize it with. We'll understand this in depth when we are doing hands-on class, and then we'll fit data and then we'll predict. You good? You good? So this is, let me show you my own little sample that I did because I read the documentation. Oh, and let me show you the API. This is how you know what you want to import from. So let me now show you my own example. So I did this like my little machine learning model with linear regression algorithm. This is me bragging, by the way. So I looked into the sklearn. I knew the algorithm I wanted to use, so I was like, oh, where does it, where is it? Check the API reference, and then you'd see like you can search for it pretty much, but I know that I'm using a linear model. So, or rather, yeah, I'm using a linear model. You know how I mentioned that there are different algorithms that you can use. Once you identify that, oh, this model is going to need maybe like clustering, right? Or yeah, sorry, if this model is going to use this data is going to need unsupervised learning, then you'd probably find yourself in, let me see, sklearn. I guess it's part where you can search. But anyway, for the linear model, I can see my, I think linear regression should be somewhere here. I really can't see. So I'm checking, I'm checking to just to Control F, linear. Okay, found it. So, oh yeah, so right there. So we have this linear regression, and sklearn, the family import model, and that's what I did here from sklearn the family import model, and then I initialize the model, right? Just like I mentioned it here, right? And then I fit the data, which I did here. I fit the data which I did here, and I predicted. I would explain why this look like this later. But just I'm just showing you. I just literally like wrote a machine learning model that predicts stuff. So yeah, um, yeah. So there are different models that you can use, and there are common models too. Anyway, so you might not necessarily need to know all of this, but it's good knowledge, anyways. So, uh, yeah, pretty much. This is, oh, and then if you want to use neural network, I'll find myself in the neural network family, and they have these things that you can use. Um, for regression, I have all these regressor models. For classification, I have all these. I have this rich classifier, SGD classifier. Logistic regression is actually a classifier, but It's a we'll dive into that later. So I'm trying to find cluster. I knew it. So this is what when I do like unsupervised learning, you'd find your algorithm in the cluster family. So you probably want to pick the common ones. DBScan is pretty common. So I could do something like from so if I want to do like clustering, I can do something like from sklearn. Although one habit you should have is this is all your inputs will be at the top anyway. I'm just like showing you. So from sklearn.cluster import what was the name? Import dbscan. So I'll just copy this. Or rather just write it. dbscan. Boom. And then I've imported it and then I can just like say dbscan equals so this asterisk I will talk more about when we are doing hands-on. This asterisk just means that your stuff is running, your processor is running. So dbscan and boom, I've initialized the model, and then if I have data I can now start predicting. That easy, really that easy to use sklearn, and that's the cool part. So dbscan is one of them. K-means is one of the common ones too. Okay, is this actually K-means is one of the common ones too. So we'll talk about these things when we get to that stage. But that's scikit-learn for you and the 3-step API. So machine learning is also like really easy once you have a data setup and you don't have to like write like overly complex system just to get your results out. Right, so we have come to the end of the class and we've discussed ML, we've discussed types of ML, the learning pattern, the types of learning patterns, EDA, we've discussed data investigation process and the scikit-learn HTML API. Thank you for coming to this class. If you don't have, if you have a few things that you don't understand, please reach out to me on Discord in the Data Epic channel. Just tag me on your questions really in the Q&A section, so I'll be able to like come by and answer them. So thank you for coming. Thanks to SlidesGo for giving me this in a very nice chalkboardy template to use. Yeah. For our next class, we'll probably go into like more hands-on stuff, like probably one of those types of ML. We'll probably go into the algorithm. So I'll pick the one of the types to go into first, and then we'll do that class. We'll talk about like the models. We'll talk about some algorithms. We'll use scikit-learn on them, and we'll also do some EDA in the process, because we have to prepare our data for Mozart always. Thank you for coming. My name is AG. Thank you for listening, rather. My name is AG. Well, you did come to class. I hope you are able to understand most of the things that have been taught, and thank you.